Hello everyone and welcome to our lecture 4. So today we'll be diving into an essential topic in computer science, sorting algorithms. So we've been through these sorting algorithms before also in our previous lectures, but we'll also learn more here. So sorting is a fundamental operation in data processing, playing a crucial role in optimizing performance for searching, organizing, and managing data efficiently. So, we'll explore different sorting techniques, analyzing their time complexity, space complexity, and real world applications. Okay, now Now let's shift our focus on counting sort, an efficient non-comparison sorting algorithm. Unlike traditional comparison based sorts like quicksort or merge sorts, counting sort works by leveraging the frequency of elements in a dataset rather than making direct comparisons. So, here first of all, counting sort assumes that each element in the input is an integer ranging from 0 to k, where k is a variable that represents the maximum possible value. Then second is instead of swapping the elements, counting sort determines the position of each element by counting the number of times each value appears in the dataset. Then to analyze its efficiency, we consider if nk a function of both the input size and the range of values. This method is particularly useful when dealing with datasets where the range of numbers is not significantly larger than the number of elements, and which makes it an big O n plus k time complexity algorithm, which is faster than big O n log n sorts under the right conditions. Okay, we'll now break it down step by step. So we require three lists to function. So counting sort requires three lists to function effectively. The input list length n. This is the unsorted array containing the numbers that we need to be sorted. Second is length k, a workspace list. This auxiliary array is used to keep track of the frequency of each number in the input list. Third is the sorted output list. This is where the final sorted numbers will be placed. Then if we see step by step, we first scan the input list and count how many times each number appears. These counts are stored in our workspace list, indexed by the numbers themselves. So we then modify the count list to store the cumulative count, which helps determine the position of each number in the sorted output. And then we iterate through the input list in reverse order, placing each number in its correct position based on the count list. This ensures stability, meaning that identical values maintain their original order. Okay, now let's see here. First step, input list, we have 132.153. Now count the number of instances of each value. The goal is to determine how many times each number appears in the input list. So we create a count array for frequency array where the index represents the value from the input and the value at the end at that index represents the number of occurrence. So first one, on first encounter 1, it increments count 1. then it becomes 1, and it encounter 3, it increment and count 3. So let's see here. So if you look at here, for index 2 it is adding 1. For index 1 it since for index 1 we have 2, and since we have like 0 0 plus 2 is equal to 2, and then for index 2 we have 2 plus 1 equal to 3, then for index 3 we have 3 plus 2 equal to 5, and then index 4 we have 5 plus 0 which is equal to 5, and for index 5 we have 5 and 1 equal to 6. So this is how we are doing we're doing the calculation step by step. Now it starts from index 1 and add the value of the previous index to the current index, and this accumulates the counts, giving us the total number of elements that are less than or equal to the current index. Now so here let's see in this slide now. Here after all this counting and increment, we are generating the sorted output. So now that we have prepared the cumulative count array, it's time for the final step. So here we're building the sorted output. So we have this input list A and cumulative count array 0 to 3 5 5 6. So this is our cumulative count array, and then there should be another output array which is initially empty. Now how it works: so we process the input list from right to left. This helps maintain the stability of the algorithm, meaning that elements with the same value retain their original order. Now for each element aj in the input list, on step 1 it used the cumulative count to find the correct position, and if you look at here, we find the correct position using this b c a j equal to aj, and then on step 2 it decreased the count by 1, where we have caj equal to caj minus 1. And then on step by step example, if you see, we start from a6 which is equal to 3. Place 3 in position c3 which is equal to 5 b5 which is equal to 3. So decrease c3 to 4. Then on next a5, decrease c5 to 5. Then next a4 which is equal to 1, decrease c1 to 1, and then continue this process until all elements are placed. So this is the final sorted output here. So this placement step takes big O n time because we proceed each element exactly once. So combined with the previous steps, the overall time complexity of counting sort is big O n plus k. So basically the input was 132153 and the sorted output is 11233 So the time complexity, as I said, the counting phase we took big O(n). For cumulative count phase, it took big OK, and the placement phase took big O(n). So overall time complexity was big O(n) plus k. So where we have n is equal to number of elements in the input list and k the range of input values. Now is it better than merge sort? So basically, it is extremely fast when k is small compared to n. Non-comparison based works on counting occurrences rather than comparing elements, and it maintains the order of equal elements, which makes it stable sorting. And on merge sorts, it consistently efficient regardless of the data distribution, better for large data sets with a wide range of values, and it require additional memory for merging. So how can we use it, or how can we know if it is better than merge sort? So for some specific criteria or some specific cases, it is ideal. Uh, for example, like sorting integers or categorical data with a limited range. So it is ideal for this kind of problems, and also scenarios where stability is important. Stability, and applications like radix sort, where counting sort is used as a subroutine, but it is not suitable for large data sets with a huge range of values, high k. And also it is not suitable for sorting floating point numbers or complex data types without modifications. Okay, so if we compare the time complexity for merge sort and counting sort, um, merge sort is the best case. The average case and worst case time complexity for merge case is big O n log n, as we also learned it from our previous lecture. And the comparison boils down to this question, like if counting sort is faster or not. um, well, in simpler terms, counting sort outperforms merge sort when the range of values k is small relative to the size of the data set. And when k is less than or equal to n, we have big O n plus n, which is equal to big O n, which is linear time. So this is significantly faster than merge sorts, especially for large data sets. Okay, so before we wrap up the counting sort, it is important to highlight one of its most valuable features: stability. What is a stable sort? A stable sorting algorithm maintains the relative order of records with equal keys or values. So in simpler term, if we say if two elements are equal in the input array, they will appear in the same order in the output array as they did originally. So for example, if we have the input 1a, 3b, 1c, kind of like that, and the sorted output is 1a, 1c, 3b, notice that 1a appears before 1c in both the input and output. So this is because counting sort is stable. Why is stability valuable? So like so if we think about real world scenarios, we often sort data by multiple attributes. For example, sorting a list of employees first by department and then by name. A stable sort ensures that the name order remains intact within each department after sorting. Okay, now that we have covered counting sort here, so now that we have introduced. Okay, so now that we have that, after sorting by the units, we have rightmost digit, the list became 231, 442, 103, 153, and 123. Now I'll sort this list based on the tens place. So on step 2, we'll have list before sorting based on tens digit, and after using counting sort, we have stable sorting. So the sorted order based on tens place is 103, 123, 231, 442, and 153. Notice that how the relative order of elements with the same tens digit remains unchanged. This is the effect of using a stable sort. Now, if we sort by the hundreds place most significant digit, the current list we have 103, so the right one, and hundreds digits are 11241. So stable sorting again, if you do that, we'll have 10. So if we see here in this one, we'll have 103, 103, 123, 153, 231, 442, and the final sorted list. So this is we did based on the hundreds digit, so 11124. Now if you look at here, this is the final one, but we haven't done any comparison yet. Well, we have successfully sorted the numbers here, but using Radix sort, but you might have noticed something interesting. We didn't perform any direct comparisons between the numbers. So why there is no comparison? Well, unlike algorithms like quicksort or merge sort, which rely on comparing elements to determine their order, Radix sort organizes data based on the individual digits of the numbers. Now each digit is sorted independently, and the overall sorted order emerges after multiple passes through the data. So this is what makes Radix sort a non-comparison based sorting algorithm. So maintaining previous order, when sorting by the next significant digit, the algorithm relies on the order established in the previous pass. For example, when we sorted by the tens digit, we needed the units digit order to stay intact for numbers like 123 and 153. And Radix sort can be thought of as sorting of multiple levels digits. So stability ensures that earlier sorted digits, less significant, aren't disrupted when sorting on later digits, which is more significant. So here we'll see the time complexity. If you see running time of the core algorithm, it relies on a stable sorting algorithm like counting sort to process each digit. The running time of counting sort is big O n plus k, where n is the number of elements to sort and k is the range of possible digit values. Now applying counting sort for each digit, Radix sort sorts the entire dataset d times, where d is the number of digits in the largest number. Since counting sort runs in big O n k, n plus k time for each digit, and we have d digits to process, the total running time becomes big O d n plus k. So now that we have explored the time complexity of Radix sort, let's see when it achieves linear performance and how it compares to counting sort. So here we have Radix sort can achieve linear time complexity under specific conditions. When d is a constant, the number of digits doesn't grow with n. Well, when k is equal to big O n, the range of digits is not significantly larger than the number of items. In such cases, the time complexity simplifies to big O n. Now, this happens because d and k are treated as constants, making the big O d n plus k expression reduced to big O n. Now, why is there a larger constant compared to counting sort? While Reddick sort achieves linear time, it often has a larger constant factor due to like multiple phases where Reddick sort requires d passes over the data, whereas counting sort requires only one pass. And also, like each pass involves additional operations such as table sorting and digit extraction. So, although both can be linear in time complexity, counting sort is typically faster for small datasets or datasets with a small range of values because it avoids the repeated passes that Reddick sort requires. So, what's the advantages of Reddick sort over counting sort? Well, Reddick sort shines in scenarios where counting sort would be inefficient. So, first of all, it handles large ranges efficiently. So, counting sorts performance drops when k is large because it requires a count array of size k, where Reddick sorts breaks the data into digits, reducing the dependency on k. Okay, let's now look at the merge sort. So we already went through merge sort when we learned about divide and conquer technique in our previous lecture, but we'll now learn about merge sort individually. Here So we already know merge sort uses a divide and conquer approach where it splits the list into two halves recursively until each sublist contains a single element. Then it sort and merge these smaller lists back together, and merging continues until the entire list is sorted. So merge sort builds a tree of recursive calls. Each level of the tree represents a division of the list into halves. So the height of the tree is log n because the list is repeatedly divided by 2. Now this structure is independent of the list's original order. Whether the list is sorted, reversed or random, merge sort always build the same recursion tree. So the log n term comes from the number of times the list can be divided in half before reaching individual elements. Since this division process happens regardless of the data's structure, the log n factor is always present in the time complexity. And after dividing, merge sort starts to merge the sorted subsets or sublist, and this process requires comparing elements and combining them in the correct order. And the merge step runs in linear time for each level of recursion, which is big O n. Like the recursion depth, this step is unconditional, it always happens no matter the data. So the total running time is the product of the depth of the recursion tree, which is log n, and the work done each level n. So this gives us the final time complexity, which is big O n log n. Okay, now we'll also look at quick sort, which is fast but with a twist. So as you already learned about quick sort in our previous lecture, so we'll just go through here with an example. Well, it is a recursive procedure and we have to select a pivot somewhere in the list. Let's say we selected 4. Then we'll move the pivot to the right side of the list, setting it aside, and establish an imaginary wall on the left side. Now begin comparing the pivot to elements in the rest of the list. We can start with the leftmost index. So when the element is greater than the pivot, leave it on the right hand side of the wall. So we'll see. We'll move on to the next element now. When the element is less than the pivot, swap it with the leftmost item on the right side of the wall. So we swapped it. So we'll then shift the imaginary wall to the right, and this maintains a property we need, like everything on the left hand side of the wall is less than the pivot, and everything on the right hand side of the wall is greater than the pivot. Now check the next element in the list, which is 2, which is less than the pivot. Now we'll swap with the element on the right side against the wall. So then we'll shift the wall once again to maintain the property. Now with the next element, we find it is greater than the pivot. So we don't need to move it any further. And remember, we are not sorting these individual elements directly. We're just maintaining the property around the wall. Finally, the 8 is on the proper side as well. So we are finished almost. We now need to put the pivot in the proper position. So we'll place the pivot on the left hand side of the wall, and this positions it in between everything greater than and less than it. Now pivot is in its final position. Finally, recursively quicksort the left and right partitions. If you look at this, if you see on the right side of the wall, we have all the values which is greater than the left side. Now we'll repeat the recurrence until the list to be quick sorted only has 1 or 0 elements remaining, or until no swaps needed to be performed. So then we'll perform swaps so that elements larger than the pivot are on the right side, while elements smaller than the pivot are on the left side. Then recursively quicksort the left and right sides, selecting a new pivot for each, and we'll continue until pivot is the last element. Now we can say, like after completing a single call to quicksort, the pivot element will be in its final position in the list. This is guaranteed. So everything less than the pivot is to the left, and everything greater than the pivot is to the right. And when performing the recurrence, a new pivot is selected. The pivot is once again guaranteed to be placed in the correct final position, and then will terminates either when the list is sorted or when we have manually sorted each node into its proper position. So here we have each recursive call reduces the size of the partition, and then we have worst case, best case, and this is the equation for worst case, best case. And so what happens on average? Well, real world inputs rarely cause worst case behavior, and random pivots generally result in partitions that are reasonably balanced. Now expected recurrence relation could be like tn by 2 and plus t 3n by 4 plus big O(n). So on average, the pivot doesn't perfectly split the array but avoids extreme imbalances. So even with uneven splits, the depth of the recursion tree is big O log n, and each level performs big O(n) work. Okay, balanced partitioning. What is balanced partitioning? Um, Here we'll look at balance partitioning. Mm, Now that we have explored quicksort's behavior with different pivot choices, let's take a deeper look into how balanced partitioning affects its performance. Specifically, what happens when the partitions are not perfectly balanced but still better than the worst case. So, first of all, um, let's understand the scenario. Imagine a partition where 9 by 10 of the array always ends up on the left hand side and 1 by 10 of the array goes to the right hand side. This is better than the worst case scenario where one side has n minus 1 elements and the other has 0. But it's not as balanced as the ideal case where both partitions are equal n by 2 on each side. So if we just quickly recap of partitioning impact, like um, perfectly balanced partition n by 2 each side, so the time complexity will be big O n log n. This is the best case scenario for quicksort. And highly unbalanced partition n minus 1 and 0, for this the time complexity will be big O n square, which represent the worst case scenario. So in this case, the recursion tree becomes deeper because the larger partition, like 9 by 10 of the array, keeps requiring more recursive calls. However, since the smaller side reduces quickly, it's better than the worst case. Okay, now we've established that the partition splits the array into two parts. Now, the recurrence relation for this partitioning scenario is Tn equal to T 9 by n by 10 plus T 9 by n by 10 and plus big O n. Now here T 9n by 10 and T n by 10 represents the recursive calls to the left and right partitions, and big O n accounts for the time required to partition the array at each step. Now to solve this recurrence relation, we use the recursion tree method. Each level of the recursion tree represents the work done to partition the array. So as we go deeper into the tree, the left side reduces by 9 by 10 each time and the right side reduces by 1 by 10 each time. So the work per level stays proportional to n, but the tree's height increases compared to a perfectly balanced partition. So then after expanding the recursion tree, we find that like the time complexity result is Tn equal to big O n log n. And despite the imbalance in partitioning, the logarithm depth is still maintained. And this happens because the smaller partition 1 by 10 of n shrinks rapidly, keeping the recursion tree from growing too deep. So the constant hidden in the asymptotic notation is larger than in the perfectly balanced case. However, the overall asymptotic time complexity remains the same. And this means quicksort's performance is robust even when partitions are not ideal. So we can say about 80% of the time the partition will produce a split that's more balanced than the extreme like 9 to 10 or 1 to 10 ratio in real life, in reality. But this is because when choosing pivots, especially with randomization, most splits naturally fall closer to balanced. So on average, the asymptotic bound remains the same as in the best case scenario, And this holds true because the majority of partitions aren't significantly imbalanced. Even when imbalanced, the recursion tree depth doesn't grow enough to shift the asymptotic time complexity. Okay, now we know two key facts now. That first of all is quicksort performs exceptionally well with large data sets that have a uniformly random distribution. It is great for general purpose sorting due to its efficiency in leverage cases, and insertion sort shines when dealing with small data sets or nearly sorted list. Now, if we try to combine these two, we can combine quick sorts efficiency for large data sets with insertion sorts speed for small data set. And this leads to a well-known optimized algorithm, IntroSort, or a similar hybrid approach. Okay, now let's shift our focus to an optimized variant of quicksort known as randomized quicksort. This technique addresses one of the key weaknesses of the traditional quicksort algorithm, its vulnerability to poor pivot choices. So, why randomize? Well, in quicksort, if we consistently choose poor pivots, like always packing the smallest or largest element, um, um, so we end up with highly unbalanced partitions. This leads to worst case performance. So to solve that problem, we can use randomized quicksort, which eliminates the risk by randomly selecting the pivot. Now, this ensures that no specific input can constantly cause poor performance. Now, instead of picking a fixed pivot like the first or last element, we randomly select an element from the array. And this random selection step can be performed in big O one time. And then we can partition the array around the randomly chosen pivot, and this step is performed in big O n time. And then we'll apply randomized quicksort recursively to the left and right partitions. Importantly, for each recursive call, we again randomize the pivot selection. Well, I will add a pseudocode for randomized quicksort in the lecture in Moodle, and so basically, like it is powerful because it is like input data cannot be crafted to force the algorithm into worst case behavior, because it is unpredictable. It could be anything, any random value. So it is also very simple, like it adds minimal overhead compared to traditional quicksort, and performs exceptionally well on large data sets, even outperforming other big O n log n algorithms in real world scenarios. Um, so first of all, um, it is we can give a practical example, it is used in standard libraries for randomized algorithms like Python sort for certain data types, kind of like that. um, to conclude this lecture, we'll see um, randomized quicksort combines the elegance of quicksort with the robustness of probabilistic algorithms. It ensures high performance across all input types, making it a favorite in both academic study and real world applications. So that is the end of this lecture, but um, if you have any question regarding this lecture, please feel free to email me, or um, just post a question on the discussion forum. um, Please watch the recorded lecture properly, if you want to understand, because that's a very difficult topic. This is a very tough course, because you have to understand more in this course. And if you need any help, I am here. And I will give homework, or I mean assignment 1 this week. I'll publish it this week and it will be due next week. So make sure you properly understand the homework, and if you have any problem with the homework, feel free to reach out to me. And I will try to reply to you as soon as possible. Thank you.